Uh, in fact, 12 was very in depth, and I'm starting off with 12, the basic rules, and it's very interesting because it's quite simple. And if you can understand 12, 22 will become very easy. I think what you can do is you can go on the net and you can download ISO 15189 2022. I have a copy with me somewhere. Maybe we'll talk about that a little later. I found that it is a little easier said than done. To compare it, I think it's easier than 12. 12 is very much in depth, and that's the reason why I'm starting off with certain bits from 2012. I think we can start with the first. All right. So this is ISO 15189 2012, and this is the technical section 5.6. In fact, I told you last time that your ISO 15189 is divided into many sections. Section 4 deals with the management aspect, and 5 deals with the technical aspect. And then, of course, you've got the scope and you've got terms of references and stuff like that. Now, this is 5.6, is a technical section. Ensuring quality of examination results has 7 subsections. Take a look. Quality control materials, quality control data, interlab comparisons. We are going to do that interlab two Thursdays later. Alternative approaches, analysis of inter-laboratory comparison samples, evaluation of laboratory performance, comparability of examination results. This presentation deals with the first 2 sections, quality control materials and quality control data. All right? But keep in mind, 5.6 has all these subsections, 7 subsections, and it becomes very, very important. You can download 2012 also. Usually we have these books printed and we keep it with us. All right? And in this little graphic circle up here, what have you got? You've got quality control at the base, you've got quality assurance, and you've got quality management systems. And we will take a look at each as we go along. All right? In the next PPT slide, we are going to laboratory quality control. What is it? We're asking the question. That is the most important thing, right? Laboratory quality control is designed to detect, keep it in mind, to detect, reduce and correct deficiencies in the laboratory internal analysis process prior to the release of patient's results in order to improve the quality of the results reported by the laboratory. So when a diagnostic test is performed in the medical lab, the outcome of the test is a result, right? The results may be patient result or it may be a quality control result. The result may be quantitative, a number, or qualitative, positive, negative, or semi-quantitative, limited to a few different values. So get familiar with these terms. Why are we using quality control materials? The first line tells you to detect, reduce, and correct deficiencies in the laboratory's internal analytical process. Because somebody can come and tell you, a patient can come and tell you, I don't believe what you have given me. It's all nonsense. How do you convince him if he's ready to listen to you? So if you have these internal controls that you run on different levels, you've got your mean SDCV, you know that the day's quality control results were absolutely on target, and the results coming out henceforth of your patients are correct. Because if your internal quality control is not working properly, it's out of range, then chances are your patient's results are not correct, and you can be challenged. And this is what happens, and this is what was happening. Somebody having a sugar done in one lab, the sugar was 70, Then he goes to another lab, it's 90. He goes to third lab and it's 100 and something. Which lab is correct? That's how this evolved over the years. And I remember when I was a student in the 70s in America, this was just getting to be, was fructifying. And we had to maintain the data, and it helped quite a bit. All right. So we said, so when the diagnostic test is performed in the medical laboratory, the outcome of a test is the result. Somebody is coming in. Who is it? Okay, admit him. All right, Gautam Bhai is in. All right, so we're coming back to our slide. So when the diagnostic tests is performed in the medical laboratory, the outcome of the test is a result. The result may be a patient's result, or it may be a quality control result. The result may be quantitative, qualitative, or semi-quantitative. All right, depends on what you are looking for. And let's take a look at the little color balls at in the middle. So you've got quality control in the middle. All right, so you've got the material, you've got the method, you've got the machine, and so on. So all are interdependent, because if you're using machines, you will need very, very good quality control. One more person will be written. Nazdeen, all right. Nazdeen, welcome. All right.
Hello, ma'am.
Yeah.
Good afternoon.
Yeah. We've just started.
Yes, ma'am. I'm
Okay.
also at home.
Okay.
So I
Let's go
wanted
to
seek
the other
your
slide, slide 4. So we are asking, what is this quality control, etc. used for? So QC results are used to validate whether the instrument is operating within predefined specifications, inferring that patient test results are reliable. As I told you, you can be challenged. So you first have to know that what you are putting out is reliable. Once the test system is validated, patient's results can then be used for diagnosis, prognosis, and treatment planning. For example, when a patient's whole blood is estimated for hemoglobin, the test results tell us how much hemoglobin is present in the blood, the concentration in grams percent. The result is then used by the physician to determine whether the patient has a low, normal, or high hemoglobin. Is he anemic or is he normal? And you know that the hemoglobin is such a basic test that is done every day. Especially now with the advent of machines, you will need, at least in hematology, ideally 3 levels of control, but at least you should use 2. So quality control, the whole process. Again, you remember my very first lecture, we went through this pre-analytical, pre-analytical, analytical, post-analytical, and post-analytical stages. All right. So even in labs, in biochemistry, in hematology, we get into this every step, at least 5 of them. All right. So we are asking the question, what are these QCs made up of? So quality control products is a patient-like material, ideally made from human blood, serum, urine, or spinal fluid. The control product for hematology is a liquid material and contains formed elements of blood. Control products should be tested in the same manner as the patient samples. Now your chemistry controls are lyophilized. Once you reconstitute, what we do is we aliquot them and we freeze the aliquots and we take out one Eppendorf every day. Let it come to room temperature, and then we do the testing after half an hour or so. As against your hematology controls, they are good once you open the vial, because it's a liquid. You cannot freeze it because you'll lyse the blood. So once you open the vials, they're good for about 9 to 10 days because we don't want lists to set in, and they are expensive depending on the machine that you are using. It's worth spending on these quality control in hematology and very good quality control in the biochemistry and so on. So we said quality control products should be tested in the same manner as patient samples. All right. Again, we ask the question, is regular testing needed? Of course, because you've got to run this every day. How do you know that the results you're putting out are correct? Good laboratory practice for hematology requires testing normal, abnormal, and subnormal controls. So I told you need 3, or at least a minimum of 2, for the CBC daily to monitor the analytical process. Regular testing of quality control products creates a QC data base that the laboratory uses to validate the test system. Validation occurs by comparing daily QC results to a laboratory defined range of QC values. The lab defined range is calculated from QC data collected from testing of normal and abnormal samples. So when I'm using creates a database means you need a logbook, you can write it down.
Dr. Shubha is calling.
She's calling doctor. All right, you can talk. Just a moment, Dr. Shubha's calling.
Okay, I'll send.
Guys, just hold on. Be patient.
Okay, I'll send you the link. Okay, I'll send you the link.
All right, so we said
Huh.
what we do is once we run the 3 levels or 2 levels, we log it down. We put the date and we log down the values. All right. Your data, they will supply the manufacturer will supply you with his own data sheets. Don't go by it. You produce your own data and log it down, because at the end of the month, after 10 days or something, you can have your own mean SDCV. Validation occurs by comparing daily QC results to a laboratory defined range of QC results. The lab defined range is calculated from QC data collected from testing normal and abnormal controls. So you will run, I told you, 3 levels or at least 2 levels every day, and you will document it in a regular logbook, or you can document it on your laptop. And nowadays, most machines have their own Levy Jennings incorporated into the system. So we come to the 8th slide, and the heading is comparison of quality control results to specific statistical limits. Let us assume that there are 2 ranges reported on X parameter. The acceptable range for level 1 for the normal sample of hemoglobin is between 12 and 14 grams per cent, and the abnormal level is between 16 to 18 grams per cent. When the daily QC result obtained from the normal control is compared to the range calculated for the normal control, it becomes apparent that each result lies somewhere within the expected range. All right? Because your manufacturer will supply you with a log, and it will tell you this is supposed to be the range. So this is a guide for you that as long as your QC value falls within that range, you're on the right track. You log down what you got. This indicates that the analytical process is in control at the normal level of the day's testing. When the daily QC results from the abnormal control is a high hemoglobin is compared to the defined range for the abnormal control, the analytical process is shown to be in control for each day of testing, except for the last day. All right, we'll see why. Okay, so you're buying your control from the dealer. He will supply you with his own literature, where you will know that this should be the range, and as long as your values fall within the range, you're on the right track, whether it's the normal what you're using or the abnormal. This continues. QC statistics for each test performed in the laboratory are calculated from QC database collected by regular testing of controlled products. The data collected is specific for each level of control. What happened? Okay. Let's go back. Dr. Chogle has come in. Alright, so I'll repeat again. QC statistics for each test performed in the laboratory are calculated from QC database collected by regular testing of controlled products. The data collected is specific for each level of control. Consequently, the statistics and ranges calculated from the data are also specific for each level of control and reflect the behavior of the test at specific concentrations. Okay? Have you understood so far, or you're puzzled? Any questions? Because we're coming to a little bit of statistical parameters now. Parul, Meena, Fariza,
Yes, ma'am.
Nazreen, you're familiar with all this?
Yes, ma'am. Yes, ma'am.
Huh? Okay. So we come to this mean SD and CV. So it's a bell curve up here that you've got. The most fundamental statistics used by the lab are the mean, that's X, and standard deviation S. The mean or the average is the laboratory's best estimate of the analyte's true value for a specific level of control. To calculate a mean for the specific level of control, first add all the values collected for that control. Correct? Then divide the sum of these values by the total number of values, right? I think you all know how to calculate mean. So you've got 10 values, 10 different values. You add up those values and you divide by 10 and you will get the mean. All right? That's simple. Then you have calculating standard deviation. Now this is a very important parameter. Standard deviation is a statistics that quantifies how close numerical values are in relation to each other. The term precision is often used interchangeably with the standard deviation, so keep it in mind. Okay, precision. Another term, imprecision, is used to express how far apart numerical values are from each other. Standard deviation is calculated for control. Who is it now? Dr. Shanti? Yeah. Who's it? All right, where are we? Okay. Another term, imprecision, is used to express how far apart numerical values are from each other. Standard deviation is calculated for control products from the same data used to calculate the mean. It provides the laboratory an estimate of test consistency at specific concentrations. So keep in mind, your SD tells you the precision of your data runs. And of course, there's a formula at the bottom. It's a square root. You can take a look at it. Okay. So we said, what does it say? Standard deviation is a mathematical expression of the dispersion of a group of data around the mean. Keep that in mind. I'm repeating, is a mathematical expression of the dispersion of a group of data around the mean. All right. So here you have the root. All right. We'll continue. The repeatability of a test may be consistent, low standard deviation, low imprecision, that is what we want, or inconsistency, high standard deviation, high imprecision. We don't want that. Inconsistent repeatability may be due to the chemistry involved or the malfunction of the instrument. If it is malfunction, the laboratory must correct the problem. It is desirable to get repeated measurements of the same specimen as close as possible. Every day that you do it, Even if you run it 3 times a day, it should be as close as possible. So use of standard deviation, please keep it in mind. Once you've determined the standard deviation, must use the information to evaluate current or future analyses. Most labs make use of 1 plus or minus 2 SD or 95% confidence limit. To put this into a workable form, you must establish the range of plus minus 2 SDs. So how do we establish that? Your Levy-Jennings also becomes important now. So we ask the question, why do you need good precision? Because you want repeatability, right? You don't want your values varying 10 times a day or 10 times a month. Good precision is especially needed for tests that are repeated regularly on the same patient to track treatment or disease progress. For example, an anemic patient has a hemoglobin of 4 grams percent, and this is a critical result, right? It's very low. In this case, the hemoglobin, to be precise, is important because lack of precision can cause loss of test reliability. If there is a lot of variability in the test performance of hemoglobin, it will be different at different times, right? So one day you are getting 4, next day you're getting 5, next day you're getting 10, and this is not acceptable. So high imprecision, high standard deviation. An example of good standard deviation may also be used to monitor ongoing day-to-day performances. For instance, let us assume that to be true in the extreme case. During the next few weeks of testing, the standard deviation calculated in the example for the normal hemoglobin control increases from 0.08, it doubles to 0.16. This mostly indicates a serious loss of precision. This stability may be due to malfunction of the analytical process. We said that it could be the machine, it could be your reagents, it could be anything. Investigation of the test system is necessary, and the following questions should be asked. Has the reagent or reagent lot changed recently? Has maintenance been performed routinely and on schedule? So this, guys, if you have a machine, you have to have an AMC, an annual maintenance contract, where the engineer will come every 3 months or 6 months, and they will do the maintenance. And once the maintenance is done, you have to calibrate and you have to run your controls and see what readings you're getting. So if you haven't done the AMC, then chances are you're going to get imprecise results. Of course, the reagents also play a great deal in that. Some cleaning or replacement necessary, we are asking the question. Are the reagents operating correctly? Has the test operator changed recently? That can happen. So we said we will need to create Levy-Jennings charts. Creating a Levy-Jennings chart, standard deviation, is commonly used for preparing Levy-Jennings charts, LG charts as we call them. Levy-Jennings chart is used to graph successive run-to-run or day-to-day quality control values. A chart is created for each test and level of control. The first step is to calculate decision limits. These limits are plus minus 1s, plus minus 2s, plus minus 3s from the mean. The mean of level 1 of hemoglobin control example is 12.1 and the standard deviation is 0.1. And this is what you track day to day, month to month. You can't have this changing. So 1 to S, plus minus 2s, plus minus 3s, quality control limits are calculated. Levels drawn on either side of the mean. So let's enlarge that graph below. Can you see? You've got the mean and you've got a line on the plus, your plus 2SD, and you've got a line on the minus 2SD. We call this positive bias, negative bias. And you can see how your control has run day to day. Up, down, up, down, up, down, and then you've got 2 outliers. It's gone outside 2SD, which we don't really like, and you've got one again nearly touching 3SD. And you have different batches running at the same time, okay? So when an analytical process is within control, approximately 68% of all QC values fall within the plus or minus 1 SD. Likewise, 95.5% of all QC values fall within plus or minus 2 SD of the mean. About 4.5% of all data will be outside plus or minus 2 SD limits when the analytical process is in control. So that is also acceptable. Approximately 99.7% of all QC values are found to be within plus or minus 3 SD standard deviations. And usually, at least we don't like it. We like our values to be on plus minus 2 SD at the most. Only 0.3% or 3 out of 1,000 points will fall outside plus or minus 3 SD limit. So that's out. Any value outside plus or minus 3 SD is considered to be associated with a significant error condition, and patient's results should not be reported. So keep that in mind, all right? So here is expanded the Levy-Jennings chart. You've got the mean at 0. You've got the dates at 1, 2, 3, 4, 5, 6 that you're reading, and you've got the values up, down. Usually it has to be, we don't want a shift or a trend. We want the values going up, down, plus minus 1 SD. And you've got one value between 1 and 2. Can you see that? Minus SD. You've also got some values between 1 and 2 SD, the positive bias, all right? Would you like to take a look at the Levy-Jennings again? Keep it in mind. And like I told you, most modern machines have it inbuilt. It will automatically log it in, all right? Using a Levy-Jennings chart to evaluate run quality. The laboratory needs to document that quality control materials are assayed and the quality control results have been inspected to assure the quality control of the analytical run. Now this is the job of the lab manager at the beginning of the day, middle of the day and end of the day. And this has to be documented because when your assessors come from NABL or CAP, they will take a look at the log. Similarly, when you do an internal audit, your internal auditors take a look at this and they will point it out to you and tell you, hey, what you're doing is not correct, please start all over again. The QC log can be maintained on a computer or a paper, like I told you. The log should identify the name of the test, the instrument, units, the date the test is run, the initials of the person performing the test, and the results for each level of control assayed. And this again, not only is the job of the technologist, it is the job of the quality manager to see that this is run every day, and he or she has to approve the QC for the day. Then only ideally the other parameters, the other test samples can be run. If the QC for the day in the morning is not correct, it's falling outside plus minus 3, then usually when I was lab manager, I have on occasion stopped the whole run. I know my techs didn't like it, but then I said, no, hold on. Let's scrap this and run it all over again. Because we were into NABL at that time. We were also doing CAP and we performed pretty well. All right. So these are your different types of, we'll see this, what Westgard rules say. We said you've got a 1-2S violation, you've got something falling outside of 2, then you've got a 1-3S violation, you've got this, then you've got a trend at 10 points outside the mean, this is not allowed. Then you've got systemic error, you can see. You've got 7 results falling in pattern, up and down, and we don't like it. So shifts and trends come into play. Again, at the chart below, you can see that there is a point going outside, I think 3S. All right. So you come to what is known as systemic error and a random error. A systemic error is evidenced by a change in the mean of the control values. The change in the mean may be gradual and demonstrated as a trend in control values, or it may be abrupt and demonstrated as a shift in control values. So trend slowly moves away and you've got a shift, that is a sudden drop or increase. Get familiar with this terminology. Trend. The trend indicates a gradual loss of reliability in the test system, and we don't like it. Trends are usually subtle. You have to chase, you have to watch what's happening. Causes of trending may include why is it happening? Deterioration of the instrument light source, gradual accumulation of debris in sample or reagent tubing, gradual accumulation of debris on electrode surfaces, and that's bad. Aging of reagents. So you haven't changed your reagents, you're using old expired reagents. You're not cleaning your machine, you haven't had your annual maintenance done. Those little bits that a tech has to do every day to look after his or her machine. So now you've got a systemic variation. So you've got a trend, keep that in mind, resulting change gradually in either direction, indicating slowly changing parameters, deteriorating reagents, equipment failing. And you've got a shift, a sudden. Results fall sharply on one side of the mean, indicating a major change has occurred, and you have to investigate why this is happening. Both are not advisable. So then we come to a random error, which is acceptable at times. Random error is a deviation away from the expected results. For QC results, any positive or negative deviation away from the calculated mean is defined as a random error. There is acceptable or expected random error as defined and quantified by standard deviation. The expected population of data, example, data points outside plus or minus 1,3s. There is an unacceptable random error that is at any point outside the 1,3s rule violation. That's not acceptable. So now we come to Westgard rules. I'm sure you've heard of him. He is the father of quality control, as I call it. James Westgard of the University of Wisconsin published an article on laboratory quality control that set the basis for evaluating analytical quality runs for medical labs. The elements of the Westgard system are based on the principle of statistical process control used in industry nationwide since the 1950s. There are 6 basic rules in the Westgard scheme. These rules are used individually or in combination to evaluate the quality of analytical runs. Westgard devised a shorthand notation for expressing quality control rules. Most of the quality control rules can be expressed as NL, where N represents the number of control observations to be evaluated, and L represents the statistical limit for evaluating the control observations. Thus, 1,3s represents a control rule that is violated when one control observation exceeds plus or minus 1,3s control limits. So now you get familiar with his terminology. So 1981, James Westgard of the University of Wisconsin published an article on laboratory quality control that sets the basis for evaluating analytical run quality of our medical laboratories. The elements of the Westgard are based on principles for statistical process control used in the industry nationwide. There are 6 basic rules in the Westgard scheme. These rules are used individually or in combination to evaluate the quality of analytical runs. All right? So here you've got the Westgard rules, what is approved and what is rejected. So you've got multi-rule, uses a combination of decision criteria on control rules, allows determination of whether an analytical run is in control or out of control. So you can run 2, 3 known controls and you take a look, as long as they fall within the accepted parameters, you know that it is in control. If it is out, then you can say it's out of control. So either your quality control is approved or it is rejected. The rules set limits for labs to determine acceptable control values and therefore which patient results are valid. So as long as your quality control falls within the acceptable normals, right, then we say that, all right, we will accept the patient's results that are out. If it does not, then we have to reject. That's what I told you. As a quality manager, that person has to take a look at it, the beginning of the day, middle of the day, end of the day, and he or she is not satisfied, then he has to stop the process in between and start all over again. You may say it's a waste of time, money, and energy, but remember, your patient's life is most important. And if you give repeated false results, your lab is going to lose the reputation and NABL is not going to certify you. Keep that in mind. So we come to coefficient of variation, CV percent. It's a sweet little thing. Your formula is here. CV percent is 100 into SD upon mean. Remember that. CV percent is equal to 100 into SD upon mean. And your mean, SD, CV, all three parameters you can calculate using Excel. Makes it very easy. The coefficient of variation is the ratio of the standard deviation to the mean as expressed as a percentage. The CV allows the technologist to make easier comparisons of the overall precision. Since standard deviation typically increases as the concentration of the analyte increases, the CV can be regarded as a statistical equalizer. If the technologist is comparing precision of two different methods and uses only standard deviation, he or she can easily be misled. If the comparison rule standard deviation, it can be incorrectly assumed that the hemoglobin on the calorimeter is more precise than the hemoglobin on the 3 or the 5-part analyzer. If, however, a CV is calculated, it might show that both methods are equally precise. So calculate both and follow. All right? And so limits are set. I will tell you, your means should be constant. If your means are constant, your SD is constant. And if your SD is constant, your CVs will fall to a certain range. Usually for most parameters, your CV at the end of the month has to be less than 4%. Whether it is hemoglobin, red cell, white cell, sugar, blah, blah, blah. But CVs for enzymes, we give it up to 7%. As long as the CV percent is in the vicinity of 7%, we said it's fine. But the other parameters have to be less than 4%. All right? So calculation is right here, and you've got your Excel, and I'll do it for you in a second. So this is it. You've got SD, you've got mean, and you've got CV. And I always tell my techs that monitor your SD month after month, week after month. As long as the SD is constant, let us say the SD for sugar is 0.1. Then every month, every week, it has to be 0.1, 0.1, 0.15. Maximum it can go up to 0.2. But if you're getting 0.1 in June, you're getting 0.3 in July, you're getting 0.5 in December, and you've got 0.1 again. That is not acceptable. That means things are going wrong. Your means are off, your SD is off, and your CV is off. Okay, so we've got coefficient of variation indicates that the percentage of the mean is represented by the standard deviation. Reliable means for comparing the precision or SD at different units of concentration expressed as a percentage, right? So keep this formula in mind, it's very simple. Next one. So then, when you go for quality control and you go for external EQUAS, etc., you will have all these results coming through. So coefficient of variation, CVR, an easy way to make the comparison is to divide the laboratory CV, that's example 4, by laboratory peer group CV obtained from inter-laboratory comparison report. This is your EQUAS. Example, hemoglobin for all other laboratories using the same instrument, that is there you have to use the same instrument, the same methods, is 4.2%, and the coefficient of variation is 4 divided by 4.2 is equal to 0.95. It's good. Any ratio less than 1 indicates the precision is better than the peer group. Any score greater than 1 indicates that imprecision is larger. Ratios greater than 1.5 indicate a need to investigate the cause of imprecision, and ratio of 2 and more usually indicates need for troubleshooting and corrective action. So this is again a parameter we use to in the lab to see whether our values are within limits. CVR. So then we come to selecting a control product. Most important because it's expensive. And there are labs which may cut corners and use a very cheap one, and then there's trouble. Many different quality control products, known as CRMs, short form, are available for laboratories. Choosing the right quality control products requires careful consideration. Sometimes laboratory decision makers yield to the temptation of purchasing the most inexpensive product. Unfortunately, the cheaper alternative often exhibits significant limitations, such as a short shelf life after opening. A reduced shelf life can result in unnecessary waste if the laboratory cannot use all the material. Keep that in mind. So then we come to inter-laboratory comparisons, or EQUAS as we call it, inter-laboratory, we call it EQUAS. Participation in inter-laboratory quality control comparison program is highly recommended. And with NABL and CAP, you have to be into at least one program. Without such programs, the laboratory becomes a statistical island and has no means to regularly verify the reliability of its work. One of the easiest methods to assess reliability and imprecision is to compare the within laboratory method means and standard deviations to other laboratories using the same instruments and the same methods. And we are going to talk more about this in part 2. All right? So we said join the control revolution. Expensive but necessary. All right? So the procedure for PT EQUA, External Quality Assurance Scheme, is generally for participating laboratories to be sent identical samples for tests. So once you're in the program, they will send you the sample. You will run it on any one day, like a regular sample, and you will send the results out. Please do not send the sample to another lab. Do not keep repeating the sample. Whatever you've got, send it to the EQUA lab, the person where it is sent to you, the company, and within 8-10 days you'll get the result. Their results are collected and analyzed, and the results reported back to each laboratory. Anonymity is preserved by assigning each laboratory a number. Laboratories producing poor quality results can seek advice from PT scheme organizers to improve their performance. In laboratories undertaking chemical analyses, a standard method of comparison is the Z-score. There's another one. There's another thing you should keep in mind. And let's see the calculation. So this is calculated using where X is the lab result, XA is the assigned value that comes from EQUA, and SA is the assigned or target standard deviation. So the formula is Z-score is equal to X minus XA upon SA. Z-scores in the range of plus or minus 2 are satisfactory and indicate analytical accuracy. Z-scores between 2 and 3 indicate questionable results, and Z-scores above 3 are of poor quality and should not be accepted. Now, these 3 words, accuracy is how close a measured value is to the actual true value. Keep that in mind. Precise. Precision is how close the measurement values are to each other. So can you see the targets? You've got the first one, that's precise. You've got the values as close as possible. You've got accurate, which are around the target but not precise. And the third parameter you've got, it's accurate and precise, right on target. Keep this in mind. Accuracy is how close a measured value is to the actual true value. Precision is how close the measured values are to each other. Now this is something we talk in terms of bias. When we measure something several times and all values are close, they may fall, they may be wrong by if there's a certain bias. Bias is a systematic built-in error which makes all measurements wrong by a certain amount. Examples of bias: guessing one scale 1 kilogram when there is nothing on them. You always measure your height wearing shoes with thick soles. A stopwatch that takes half a second to stop then when clicked. In each case, all measurements are wrong by the same amount. This is bias. The degree of accuracy depends on the instrument we are measuring with. But as a general rule, the degree of accuracy is half a unit each side of the unit of measure. When an instrument measure is 1s, any value between 6.5 and 7.5 is measured as 7. So you can take a look at the total allowable error in the next one. So total allowable analytical error, you will get this TE or TAE is bias plus 2ST. Right? So you've got the bell curve, the Gaussian curve, you've got 2SD, and your true value is at a certain point. So the formula is TAE is equal to bias plus 2SD. Alright? Keep that in mind. So your daily QC now, everybody does not follow this, but minimum daily IQC should be included. I think now they've cut it down. 2 levels of controls depending on daily sample load, a set of replicates precision, at least 2 or 3 previous days samples for accuracy. So a set of replicates, that means one sample repeated by 2 different texts. And your accuracy is 2 or 3 previous day samples. We keep it and we run it and we compare the results. Keep it in mind. Precision, replicates, accuracy, and at least 2 levels of controls every day. This is what your daily IQC should have. And you document it because your auditors would like to see it. And they see it, and they do see it. Alright? So quality assurance. Now let's get familiar with these words. Quality assurance will deal with the maintenance of a desired level of quality in a service or product, especially by means of attention to every stage of the process or delivery of the production. And this covers IQC, EQUAS. Without the above, a lab cannot run. NABL, CAP all require a minimum of such quality control besides split sample testing. Now the split sample is, what we do besides we undergo all these testing, we send the same sample to another NABL or CAP lab. At least we do it to all parameters on the scope, and we compare our results and what the other lab gave us, and we record it. All records are to be documented. Outliers recorded and corrected with root cause, analyses, corrective and preventive actions documented. So get familiar. So once you have a non-conformance, you have to tell your auditor what was the root cause, what was the analysis that you have performed, and what is the corrective and preventive actions that in future, in the next months, this will not repeat itself, and you have to document it. That's the reason why your internal audits every month are important, and we'll talk of internal audits as a separate presentation. So now quality assurance and quality control. Keep this in mind. And I'll give you a very good example that was given to us when we were taught this many years back. Quality assurance is an overall management plan to guarantee the integrity of the system, the data. Quality control is a series of analytical measurements used to assess the quality of the analytical data. We were given this example. After World War II, America discovered that the Japanese cars were far superior to the American cars. So General MacArthur told his group of people, go to Japan and see why is it that the Japanese cars are far superior to our cars. So a group of Americans went to Japan and they waited in their visitors enclave, and they were seeing that the Japanese car, as one part processed further on the belt, 2, 3 people jumped in, looked at the whole thing, corrected what they had to correct, and then it went further to the next chamber. The same thing was done. So when the car arrived at the final, the car had very, very few faults. The car was perfect. As against what the Americans did, they started from one to the other till the car was completely done. As a result, the Japanese car, can you imagine, was far superior because it was checked at every stage. Therefore, had very few faults. As against the American cars, 1, 2, 3, 4, 5 till the final car product arrived. Same thing in the lab. We check our results every step of the way. Therefore, when the final audits come, when the final results are procured, we come out winners. Have you got the difference? Quality assurance, quality control. That is important. All right? And that's the end. I hope you have understood what we have said today. Keep it in mind. Any questions? Nazneen, you do anything differently?
No, ma'am, but I just want to introduce one. Sorry, I'm not well today. I just want to introduce one concept. Doctor, Ruzbeh ma'am, I always give this example of your Japanese cars to my students also. So I remember it very thoroughly. So I'm using that also. Why are we doing all this? We know that we have to run quality control, we have to do everything, we have to see the percentage, everything we know.
2%.
But why are we doing this actually? So if anybody can understand, can tell, then it will be great. From my point of view, I have seen that in my study, in my experience, it is we have to rule out the sensitivity of that particular machine on that particular day. The reason is we are using a lot of variables. There are some constants and some variables. Now constants are our controls, calibrators, where we know what we have to do. But variables are the ones which we cannot control. For example, staff competency, the temperature of the machine, the room temperature, humidity. My God, that Atalica and Cobas. Sometimes Cobas also behaves very weirdly at weird temperatures. And Atalica, if there is too much humidity and cold, it will not, the temperature is hot, it will not run. So these machines also need a lot of control environment. That's why lab room temperature is also controlled. So all this quality control, what Ruzbeh ma'am has explained to us, is because of that one thing which we saw right now, inbuilt random errors called bias. We know that we are using the controls and calibrators at specific levels and at specific concentrations. But how do we know that this is coming good, it's working good today? And this is the reason why we have to do quality control, to rule out and get adjusted to the sensitivity of that instrument or that reagent on that particular day. Otherwise we will not be able to get the correct, accurate report on that day. So that is why to adjust to the sensitivity of the reagent and the instrument, all these practices we have to do so that we give the correct report. The main thing is sensitivity only, what we are targeting. We are targeting deviations. A lot of we are doing CV. CV percentage is the picture of the whole critical process. We are not targeting only SD. If you go only by SD, you will get all wrong results. So CV percentage is combining SD, biases, everything, and CV percentage is a better result, which rules out that inbuilt bias error, random error. So that is why we need to do this quality control every day.
Anybody? Dr. Shobha, what's your experience?
Yes, ma'am. Good afternoon. Sorry for joining late as one of our best family friends passed away today. I was little bit.
Shubha, just hold on. Nazreen, is this Shahid Bashir somebody from your lab? Somebody by the name of
I
Shahid
think so,
Bashir.
yes. Yes, yes, yes. Yes, yes.
Okay.
Yes, yes, ma'am. Yes, Shahid is our this thing.
Okay.
technician.
So, can you hear me?
Yes, yes, please continue.
See, first of all, when I joined, I was very fresh. I finished my PhD, and I joined immediately. The first thing that Dr. KG Nair asked is, do you know what is quality control?
Sorry, one of my dogs. Just a moment.